Thanks, Thomas. I would like to start with a very big thank you to conference organizers for pulling together this wonderful meeting. I can only imagine how large was the effort. I'm very happy to be here for this meeting, and I am even happier to have this chance to give my talk exactly on Mark's birthday. So that's an honor for me to do that. And I must say that this whole project, which I'm going to, project obviously focused on ecology of movement, ecology of slugs, it has been quite substantially motivated by some of Mark's research, in particular on, you will see it later, in particular on this scent marking dynamics and its effect on animal movement. All right, so first of all, to introduce the project, it was a 4-year project with a very substantial empirical component. So we had a wonderful group of, absolutely excellent group of, of empirical ecologists. So some of them are shown here, so and others here, so 5 people altogether. They really did incredible amount of jobs. So altogether was I said that there are more than 100, but in fact it was 163 field visits, and each field visit was quite a bit of work by itself. And then along with that, we also had a small group of mathematicians, from Birmingham and from the University of Leicester, where I am. So motivation for this talk was can be linked to a very old and sort of very fundamental problem, one of most fundamental problems in ecology, how species are distributed in space. Put it simply, why at some location we have a lot of individuals and in another location maybe just a few. So the phenomenon, which is in a slightly different context, is usually referred to as pattern formation. Yeah. I'm not touching what the pattern exactly is, but it's essentially just some sort of prominent heterogeneity in the population spatial distribution. And so what I'm going to do here, I will first go through their summary of empirical findings. So to show what actually is the phenomenon, and then I will try to link it to, so patterns are observed on a relatively large scale, field scale, which means hundreds of meters or dozens of meters. And I will try to link it to show that there's a reasonable way to try to explain it, linking it to other processes that are happening on a much smaller scale, which I call microscale, so the scale of individual slug movement. Slugs don't move too fast, you know, that means that's a much smaller scale. And then I will try to use 2 actually different mathematical approaches to describe their observed patterns, and then we will see what's coming out of it. Okay. So so just motivation for that, as I said, was understanding of what the patterns are and how and for what reasons they arrive. And this is, of course, a very old problem. So the earliest paper that I mentioned here is this by Sergei and Jackson, but you know, the story has been going on for decades, and it's a really very big problem. And one reason and one explanation why it's has been so old and still very much on the agenda is because what people usually call pattern formation, it's not a single phenomenon, it's a group of phenomena, in fact, right? Because the reasons why their population distribution is spatially heterogeneous, there can be many. And in fact, at some point, I just mostly for fun, I wanted to count some of them. And I easily count, so that there was this little paper in 2016, I easily counted 12, and then I stopped, and I'm sure there are several more, maybe much more other explanations or different mechanisms. All right, and then what is interesting, and that was a more specific motivation for this project, is that while some classical theories or models of pattern formation, and probably the most classical or most well-known is Turing instability, so formation of patterns periodical or almost periodical because of Turing instability, that actually works very well for vegetation. And there has been a lot of work, especially over the last 5-10 years, predicting very nicely transition in distribution of vegetation in response to change in the climate condition and how the patterns change. And for instance, like vegetation changes from semi-arid region to temperate region and like that. But interestingly, so these theories very rarely, I mean, I'm talking about Turing pattern formation, very rarely work for animals. I'm not saying that there are no theories at all, because in fact that's where the motivation comes from. So there's this really nice bunch of work started by Mark almost 30 years ago, and then more recently picked up very effectively by Jonathan, and most recently by Valeria. So there's a group of people still exploring Mark's ideas about how patterns or some sort of pattern or aggregation in space, put it like that, can happen in space because of specific mechanism of scent marking dynamics, right? And so that was the idea of theoretical background for this project, to see how it may work for slugs, for more specific case of slugs. For, as I said, for general theoretical reasons, like what else we can say about patterns, but also for more practical reasons, because now it's the time to introduce the main character. That's the guy, just in the middle of the slide, and it doesn't look cute at all, right? Of course, people usually expect to see some nice furry animals, right? But it's different, yeah. So, but as a single guy, it's not dangerous, right? Although even a single guy can make these big holes in the leaf, right? So it's already some damage coming. But when these guys are in high numbers, which often happens, they can destroy the whole, you know, plant over the whole farm field, effectively. Okay. So, which means that in fact, apart from their purely kind of abstract interest in what the patterns are, what are the reasons for the patterns to emerge, there was a very practical motivation, in fact, because once we know how the patterns, how the strongly heterogeneous of slugs actually emerge in the field, and then hopefully next stage will be to understand where these patches emerge. So then there are biological, any kind of control, not necessarily biological, can be chemical, classical control as well. That can be made much more efficient, because once we know where the patch is, we can spray exactly in that location, not necessarily over a much larger field, right? So it's the benefits are obvious. So it's saving in costs, of course, but also saving to environment, to damage to the environment. So, and it says here that I mean, slug spatial distribution is usually stronger heterogeneous, but the reality is, in fact, before this project, the evidence of that was purely anecdotal. Right? So the farmers know that the slugs distribute heterogeneously, but there was no any regular study on that. So in that sense, this project was first of its kind. Now, okay, that's where the story starts. So now the project investigated up to, let me see, something like 6-8 specific agricultural fields. Agricultural is important, right? The word agricultural here is important because agriculture means that the fields are subjected to some agricultural procedures like plowing for a number of years, which actually results in the soil to become relatively uniform. So whatever patterns we're going to see, it's not because, or certainly not only because of the effect of the environment, right? So there's something else going on there. But okay, where are the patterns? So to understand what is the population density at a specific location, how you do it in practical, in empirical ecology, of course, it depends on their life traits or species traits. And for the invertebrates, usual way to do it is with traps. Yeah. And once you install a trap, put it there today, come back after a week, count the animals that are in the trap, and then you lose something, right? So it's a different story how to link this number of animals to what is the actual population density, but in the first instance, we can assume that's simply proportionate, right? So 5 animals means population density 1, 10 animals, which means population density twice as large. And then if you do it with only a single trap or 2 traps, you will not learn much from that. So if you want to learn the distribution of population density along a reasonably large area, you have to use a system of traps, a grid of traps. Yeah? So that's the idea. That's how I'm getting scared to use this thing. So that's the idea of the trap. So what was used in this study was a rectangular grid, 100 traps, 10 by 10. Right? So the sketch, of course, and that's how it looked in reality. Yeah, so this sort of gray spots here, they are the traps, right? So, and then once you install them, okay, fortunately it was not me, but we had a wonderful empirical people there doing a huge job. So once you install them and come back after a week or 2, what you will have a grid of numbers, yeah, 10 by 10 table of numbers. So that will be the slug counts. So 0 means none, 1 means 1 slug, and so on. And then it's a bit difficult to work with these tables. That's the raw data, right? That's what we have in numbers, 163 of them or something like that, right? It's a bit difficult to work with them, and it's even more difficult to see what's going on. So then what we did is just simply for the convenience of visualization, we applied linear approximation, right? Simple linear approximation, interpolation, and then we end up with this sort of population distribution over the area, right? And then you see it already here that in fact it's clearly not uniform. In this case, we have a clearly a high density patch here, but on overall, except for this patch, it's kind of not impressive, relatively uniform. And then it's only one example, probably not most convincing one, but if you check it through all these field visits, you will see that actually there are patches. There are patches of quite high density, and then some of them relatively stable, can remain there for weeks or even months. Some are very transient, but certainly there is a very prominent heterogeneity of the slug population distribution. And as I said, it's not okay, for the moment it's just words, but take it as granted. We sort of checked it. So it cannot be explained by the soil heterogeneity alone, because, as I said, because of the repeated processing of the soil, it's relatively uniform. It's much more uniform than the distribution of slugs as it is. So, and then of course, I mean, one reason is ruled out. So soil is unlikely to play any role, but then of course it can still be, of course, especially in case of the transient patterns, it can simply be by chance, of course, right? How can we deal with that, and how can we make it more to quantify all these figures, right? And then there are a number of aggregation indices, right? So and then the index that we used here is called well, we call it Taylor index. Essentially, this is the exponent in the power law. So if you plot the data for each of these fields, the variance or log variance against log mean, in most cases, you will see the straight line, which means it's a power law, right? That's what they call Taylor power law, and it's pretty general. In fact, I'm not saying that it's entirely universal, but it's pretty generally what's happening for broad variety of taxa, broad variety of animals. And the trick is that if the distribution is entirely random, just imagine that we spread the individuals across the field with just uniform probability, for instance, yeah, that would be exactly 1. If the slope in logarithmic, double logarithmic coordinates, if the slope is larger than 1, then it's not random. And what we observed in the data was that it's consistently larger than 1. It's not hugely large. It ranged from 1.08, something like that, to 1.40, in fact, right? And it's consistently larger than 1, which means, in fact, that something is non-linear, put it like that. Yeah, a linear system would not provide this sort of dynamics. And what can be non-linear? So one thing, and it was on the slide, but I think I forgot to say that we don't have any reproduction, right? So we are working on this data between the generations. Reproduction would, of course, make it nonlinear, but there's no reproduction there, right? So it's only a movement over not a constant number of individuals. They can die, of course, but there's no reproduction, so which means nonlinearity as a result of that can be entirely ruled out. Then what remains is movement, right? So nonlinearity must, or at least we can assume that nonlinearity must be, can be in the movement. And that means that we have some sort of collective effect, and by collective effect, I don't necessarily mean collective movement, because when we say collective movement, we usually assume correlation of velocities. So I'm using this term here in a more general sense. Collective means more like density dependence, okay? So the slugs behave, movement behavior would be different depending on how many conspecifics are in some certain area around. So, and that actually brought in the second stage of this project, where the focus was on the individual movement, right? And individual movement was, I mean, it's all because of the advances, recent advances in this corresponding technologies. So the chips or radio tags that are used to tag animals to check their movement, they became so small, it's just a couple of 3-4 millimeters maybe, right? So even though the slugs are not huge, it's pretty safe to have them chipped and then released to the field, and then you can, so that's exactly like it was. Yeah, you can use this, I'm not sure how it's called, but you can track them, how they move, okay? So it was not always that nice, by the way. So this is obviously the nice weather and daytime and sunshine. Yeah, so quite often it was, in fact, in most cases, it was done at night for some reason. So it was not that, but it's doable and it was done. And so then the next, of course, the next question was how we analyze all this movement data. And because of the nature of the data, it's, I mean, the figure may be a bit misleading. It's not like anybody who would be walking after a slug like that, right? It would take ages, right? Because they are very slow, of course. So what, what was done actually, all the slugs were numbered, and then the empirical ecologist, Emily Forbes, PhD student on the project, she checked them all in turn, right? So slug number 1, check it, put the coordinates. Slug number 2, check it, put the coordinates. And then go around all the about 30 slugs, and then come back to the first, and that will take about 30-40 minutes. So the position of each time, of each slug was checked at irregular intervals, let's say every 30 minutes or something, right? Which makes the discrete random work framework very natural to analyze the data, right? And then once we are back to discrete random, time discrete random walk, then of course it's all down to distribution of step sizes, turning angles, and in this case also the rest times, because slug does not move all the time. They can move for a while, then they can stop for a while, then start moving again. Yeah, so, and then what was interesting to see, so we had two types of releases. Two types of releases, sparse, I need 3. Two types of releases, so dense release when they were released as a group, and sparse release when they released individually. Individually means at large distances from each other. And though all the 3 components of the random walk was, quite different, in fact, quite different between the 2 groups. So which makes the existence of the density dependence obvious, I guess, okay? So then I have to speed up a little bit. Then, of course, the next question was how this difference on micro scale, different patterns on micro scale, how can it be transformed to patterns on the scale of the field, on the patterns in the distribution of much larger spatial scale on the scale of the field, so dozens or hundreds of meters. To check that, we just build the individual-based model. To build the individual-based model is not a big deal, right? What I think is where the sort of new elements here was that we introduced added a perception radius to calculate was the density around a given slug, and then the density threshold. So if the density in the vicinity of a given slug was below the threshold, then it's a what we call sparse movement, right? If it's above, then it's dense movement, and they are different, right? And then the rest is pretty intuitive. So then, now that we run this model, so what we obtain, okay, it's like that. So time is increasing from left to right. Never mind what are the moments, they are consistent with the field data. So and you see that something is clearly happening, right? So it's almost uniform at the beginning, and then patches start emerging. And that's for this model with the switching between different types of movement. And to make it more convincing, if we don't have switching, then we have is this. Yeah? You see that in this case, with no switch, just let's say any type of these two movements, no patterns emerges, right? No patches emerges. Have a switch, have pattern. No switch, no patterns. So I think it's pretty obvious that this density-dependent movement can produce patterns. So then the next stage was, again, you can make it more quantitative if you calculate another index of patchiness called Morishita index on this occasion. And for Morishita index, if the distribution is entirely random, it's about 1. If it's not random, it's larger than 1. And you see in all cases, it was larger than 1. So once again, it's clearly shows that there are patches self-organized because of the density dependence. Then, of course, checking the dependence on the parameters, so it's the patches are still there. Then, of course, the question is whether they are that patches that we want to repeat from the field or something different. And then one way to do that was to calculate the Taylor power law now for the simulated data. And the slope, in fact, is in a very good agreement with the values that we observed in the field. So then that once again, I think it sort of proves that these are actually the patterns that we want to simulate. So in fact, I think what we managed to do, that's not the last slide, Thomas, sorry, there will be one more. So, sorry. So what we managed to do, I think, so we jumped to the last conclusion. So we managed to build a predictive model fully parameterized from the data. There is no any free parameters that actually links the two scales and predict or explain, not only predicts, but also explains how the patches emerge on the field scale, yeah, which we call large scale. Okay, after all that was done, I started thinking, okay, IBM model is not good for mathematicians, right? We want to see equations, of course. And I started thinking about what could be the equation, and then I realized that, okay, it has all been done by Mark and Jonathan and others, right? So, which was just a little bit of disappointment for me, but thanks guys for a great job. So, but I mean, it's not so simple in the sense that in fact, it's a great job in the sense that, okay, it does predict pattern formation, right? It does predict formation of a patch. What is a bit of a challenge here, I think, because it links pattern formation to the odor, scent marking dynamics, but there are some parameters which I think are pretty difficult to quantify in the field. So you really need to know what is the strength of the response of the animals to marking, right? And so the density of marking. For slugs, the odor is there, they follow each other in some sense, right? But how can we quantify the strength? Possibly it can be done in the field, but you need to think about pretty elaborate experiments or something like that. What we can do instead, and I think that's where the power of this sort of research is coming out, is that if we consider two approaches together, then linking it in themselves, we can sort of solve inverse problem. And in doing that, we can actually, without any additional measurements in the field, we can estimate what is this missing information in the mean field theory, right? What is the strength of the animal response? So it's all, I mean, the last part is more like blah, blah, blah. I mean, that needs to be done more carefully, of course, but I think that's a pretty generic outcome. So to make a sensible, not only for this case, but essentially for any study, what makes it more sensible and more efficient to have not one, but two approaches coming together and then exchange information, we can get a full story, okay? So thanks, that's just some references. So thanks for listening. And the last slide is surely the most important slide here, right? Happy birthday, Mark.